Welcome, my name is Manolis Vasilakis and this is a joint work with Antonis Adonopoulos, Aris Pagourtzis and Stavros Petsalakis. The title of this talk is Faster Algorithms for K-subset sum and variations. We will now introduce the main algorithmic problem of this talk. The centerpiece of this presentation is the problem K-subset sum. This is closely related to a variety of subset sum problems, such as the classic subset sum problem, but also the equal subset sum and many more. Here we also have an instance of this problem and a solution on this exact instance. The problem is essentially like having k knapsacks where we try to fill each knapsack exactly to a given value. Here, for example, we seek to determine whether there are two disjoint subsets where the first subset sums up to 5 and the second sums up to 9. There are many early works regarding many relevant problems, but also many interesting and recent developments, such as the one regarding the equal subset sum problem, but also the FP-TASES for subset sum ratio problem. Now we will present some necessary background in order to better understand the algorithms that we will present in this talk. We start with some notation, although we will explain it as we see it in the algorithms, but the main point is to keep in mind that this symbol and this symbol is actually a pairwise sum operation. Essentially, x and y are sets of integers, and this operation sums elements from one set with elements of the other. If there is additionally an index on the operation symbol, we bound the resulting set. Now, the interesting part is that these two operations are naturally extended to tuples. Hence, x and y can also be sets of tuples instead of simply sets of integers. We assume that the audience is familiar with the fast Fourier transform algorithm, but for those that are not, just keep in mind that there is an algorithm to multiply two polynomials of degree n in time theta n log n. Now, the most important property of FFT in this talk is the ability to extend this operation to polynomials of multiple variables. Hence, if we have two polynomials a and b of variables x1 to xk, where xi is bounded by ni, we can perform k one-dimensional FFTs, and the total complexity of all these operations is O n capital log n capital, where n capital is the product of ni's. FFT and subset sum are closely connected. Indeed, if we have as an input set z containing z1 to zn, then if we compute this polynomial, which is a product of these polynomials, we can see that each non-zero term corresponds to a subset sum of our input set. Additionally, if we can recursively compute the set of subset sums of z1 and z2, which partition our input set z, then if we perform a pairwise sum operation between those two sets of subset sums, we can retrieve the set of all subset sums of our initial input set z. For example, suppose that the input set contains 2, 5 and 7. Then, by computing this polynomial, we get as a result of these terms, and notice that each term corresponds, each exponent of a non-zero term corresponds to a possible subset sum of our initial set. Additionally, note that the coefficient, in the case of the term x to the power of 7, is 2. That means that there are two distinct subset sums, each of which, two distinct subsets, each of which has elements that sum up to 7. Note however that we cannot say something about the disjointness of those two subsets. Additionally, we also see that if we have the set of subset sums for Z1 and Z2, we can construct the set of subset sums for our initial set Z by performing a pairwise sum operation between those two sets. Now, we will use a technique called color coding. This technique was firstly used for the K-path problem, and more recently it was used by Brinkman and was adapted in the context of the subset sum problem. More specifically, it was used to solve the subset sum problem for subsets of some restricted cardinality by C. The technique works as follows. We initially partition our input set to C-square subsets. We hope that we successfully split our one intended subset, where the notion of splitting a subset will be explained later. And if we have indeed split this subset, through the FFT operations we perform, and the pairwise sum operations, and these are actually interchangeable, we can produce the respective subset sum of this subset. If we repeat this enough times, we can hopefully, and by hopefully I mean with good probability, split any random subset of cardinality at most C, hence producing its subset sum at the output of the algorithm. Additionally, another technique we use is called layer splitting, where we simply split our input set Z to log-nil layers Zi, and solve the problem, the subset sum or the K-subset sum problem for each layer independently, and afterwards we'll combine these solutions to get the solution for our initial input set. The most important property for these layers is that all the interesting subsets, and all the interesting subsets of the layers, and are those that have sum at most t, and for those subsets we can be sure that they have cardinality restricted by 2 to the power of I. And we also see an example of splitting an input set to 3 distinct layers. Now we will formally define the main problem that we introduce and study, and here is the formal description, where we are given an input set of n positive integers and k targets t1 to tk, all positives, and we seek to determine whether there exist k disjoint subsets z1 to zk, such that the sum of the elements of zi equals ti for all I 1 to k. Additionally, we assume that t is the maximum of ti, of all the ti's. Furthermore, we assume that k is constant and not part of the input. And here we once again see the previous example where we are given the elements 2, 3, 5, 7, and 8, and we seek to determine whether there exist two disjoint subsets where the first one sums up to 5 and the second sums up to 9. And here the answer is positive. Firstly, we present an extension of Bellman's classic algorithm for k equals 2, but one can extend this similarly for any arbitrary k. And we can see that the final complexity of this simple extension is O(n) times t to the k. The main intuition behind our algorithms is that we can actually add variables, each of which will represent the sum of one of the disjoint subsets. Thus, each FFT operation will involve polynomials of k variables instead of a single variable, and the final polynomial, the resulting polynomial of our algorithms will contain terms, each of which will will correspond to a k-tuple, and by k-tuple we mean it will correspond to a group of k sums, each sum of which will correspond to a subset sum, and all of these subset sums will be produced by disjoint subsets. Okay, we will first present a deterministic algorithm of this time complexity. This algorithm is based on the O tilde square root n times t subset sum algorithm, which was firstly presented by Killiaris and Zhu. And the main idea behind their algorithm was that instead of computing all the subset sums of our initial input set, we can simply divide our input set, partition our input set to congruous classes, solve the problem for the elements in the same congruous class while keeping along with the subset sums the cardinality of the respective subsets, and then reconstruct the subset sums and successfully combine them to solve the problem for the initial input set. Now we present here the algorithm running for the elements in the same congruence class, where we essentially have two distinct cases. If our input is a set of a single element, we just take all the possibilities. We either add this element to none of the k subsets, along with keeping its respective cardinality, or we add it at exactly one of the subsets, and we simultaneously increase the respective subsets' cardinality. Alternatively, if the input set contains more than one element, we simply partition the input set to subsets of equal cardinality, or almost equal. The total complexity occurs to be of this one. And the main algorithm simply takes the input set, partitions the input set to congruous classes, and solves the problem for the now much smaller values, because we divided by b all our values, along with keeping the cardinality of the respective subsets. Afterwards, it retrieves the subset sums due to keeping the cardinality of the involved subsets, and at the last step we simply perform pairwise sum operations, or FFT operations. It's actually the same thing, and we successfully generate all the subset sums of our initial input set. And the final complexity occurs to be this one, which obtained by setting b to this value. And the second algorithm we developed is randomized tilde O ni plus t to the k of complexity of this complexity. And this algorithm is based on the O tilde ni plus n plus t, subset sum algorithm presented originally by Brinkman in this paper. The main idea is that we partition our input set to L layer subsets, and then each L layer subset to m small solution size subsets. We solve the problem for the small solution size subsets. We combine these solutions to solve the problem for the L layer subsets, and lastly we combine these solutions to solve for our initial input set. We first present the algorithm for the small solution size subset. Here we essentially want to find any k-tuple where all the involved subsets are disjoint and of restricted cardinality, at most c. We use the color coding technique, and we essentially perform enough repetitions to guarantee that there is high probability that there exists at least one repetition for each involved subset, which splits it. and actually not for its involved subset, but for its k number of disjoint involved subsets. Now, more specifically, we want to split, where split is defined as this one. It essentially means that every occurring subset of the partition contains at most one element of our intended subset. We want to split any k tuple of disjoint subsets at some repetition. This means that we choose any random k disjoint subsets, and we want to have a repetition that splits them all simultaneously. This happens with fixed probability, and due to this reason we can find how many repetitions we need in order to bound the error probability by delta. And if there indeed exists such a repetition that splits all these this k tuple of disjoint subsets, the algorithm successfully constructs the combination of all the combinations actually of disjoint subset sums we can obtain from these subsets. And this happens due to the FFT operations. Now we will study the case where our input is an L-layer instance. L-layer instances are defined as follows. They're either of this form or of this form. And the important thing to note is that in both cases, all the interesting subsets, and the interesting subsets are those that sum up to at most t, have restricted cardinality at most L. Now we could use the previously presented algorithm to solve these instances by by partitioning our input set to L square subsets. But there is actually a better way, a more efficient way to solve the problem for these instances, and this happens due to this inequality. This inequality is a claim from Brinkman's paper that allows us to partition our input set to less than L square subsets, and guarantees that there is very low probability to have many elements of our intended subset to any one of the zi's. In any case, what you have to keep in mind is that we can partition our input set to less than L square subsets, and actually we can partition it to M subsets, and we can do this because there is a low probability that there are many elements of our subset to any one of the partitionings. And afterwards we simply perform the previous color coding algorithm with an upper bound higher than 1. As you can see, the upper bound is gamma, and that is due to exactly this reason. And afterwards we simply combine the solutions in a binary tree-like way, and we get the total complexity of this. We get this final complexity. And now the only thing to do is partition our original input set to L layers and solve each L layer independently and combine those solutions. And the final complexity occurs to be this. And now we will see what we can do with these exact algorithms. So both of these algorithms produce a polynomial of this form, where each term with non-zero coefficient means that there are disjoint subsets, each of which sums up to Si, where Si are the exponents. Now we can use this polynomial to solve subset sum ratio. Subset sum ratio asks for two disjoint subsets of minimum ratio of their subset sums, of their sums. If we can simply have k equals 2 and search for the minimum ratio of exponents on the resulting polynomial. We can also solve similarly the k subset sum ratio problem. We can additionally solve the k partition problem, which asks to determine what is the best way to partition to k slices. For you can say we seek to determine what is the best way to partition our input set to k subsets, where we also can reduce this to the k subset sum ratio problem. And finally, we can also use our reduced polynomial to solve the multiple subset sum problem, where we simply have to maximize the sum of all the exponents, while also respecting our bounds. Finally, we present some directions for future work. Firstly, it is interesting to research whether a simpler and slightly more efficient subset sum algorithm developed by Jin and Wu can be extended to cope with the k subset sum problem. Secondly, can we also efficiently, basically within the same complexity bounds, reconstruct the solution sets? We think that this is actually very hard to achieve, mainly due to the nature of the coefficients, because in the decision version it suffices to check if a coefficient is 0 or not. If we additionally want to reconstruct the solution sets, we do not think that this is sufficient, and the values of the coefficients can actually be very large. Finally, we should also study whether we can use similar techniques. One can also study whether one can use similar techniques to develop faster FP-tasks for the subset sum ratio problem, for example. Thank you very much for your attention.
Okay, thank you for your talk, although it's a video. Is there any question in the Zoom or offline? So actually, I have a small question. Can you hear me?
Yes.
So yeah, you mentioned in the conclusion that you may expect some faster FP tests. So do you think this is feasible, or you just raised that question just for like this?
No. Actually, we think it is actually very feasible, because the current FP-tasks for the subset sum ratio have a completely different approach.
Yeah.
So we think that it is feasible. These techniques are not used in this context. The FP-tasks for the subset sum ratio problem are actually more similar to Bellman's algorithm. They do not use FFT operations at all.
Okay.
So we think that yes, there is a future there in this direction.
Okay, thank you.
Thank you very much.
So is there any other question? So if there is no, let's thank the speaker.
Thank you very much for having me.